Okay, so for example, right, so if you look at a modern CNN, right, this is meant for this a character recognition. Okay, this is how it looks. So for example, here is an input which is an image, okay, that is going in, and then similar to your MLP, you got various layers. But then in between a few things are happening which is right now not clear. For example, there is something called subsampling that is going on here. We haven't seen what that is. But there is a convolution, right, which is going on here, some 5 cross 5 convolution. That means that actually filter is 5 cross 5, right, that is what it means. And then here there is another 5 cross 5 convolution, and then there is again a subsampling which we haven't talked about. And then suddenly, right, there is an FC layer, a connected, fully sort of fully connected layer, and then finally, right, you have a classifier. Now, one of the things, right, that we should remember is that just because you have a 2D CNN, right, it doesn't mean that fully connected layers won't occur at all. Okay, inside that you can have a network that's completely sort of convolutional. Okay, those are called FCNs, fully convolutional networks. Okay, so they are like fully convolutional, end to end. Like a regression problem will typically be fully convolutional. But here that's not the case. Here your job is to actually identify, kind of recognize the input number, right. So you got like 0 to 9, and therefore, right, you have these class labels at the output. So it's a cross entropy, right, at the output, and eventually, right, you have to have similar to that one hot vector that I talked about. When you show a 0, let's say your output vector should be like 1 and then all other zeros, right. You have a 10-dimensional vector at the output. If I show you 1, then maybe you just say that the second digit should be on and everything else should be off at the output, and that's how you do a cross entropy. This we saw last time, right, and there will be a softmax and all somewhere, okay, that and all will be there. Now, one of the things, right, which is not clear is this thing. Okay, you seem to have multiple things stacked. Right, one convolution I can understand, right. I mean, if I have to do a convolution by weight sharing and locality, I can just take a kernel, do this. I can take a 5 by 5. But then you see that, right, there are multiple things stacked there. So the idea is that, right, these are called channels. Okay, these are called channels, and the idea is that, right, each channel. Okay, so for example, each channel is like an output, correct. So it's like I have applied a convolution, and whatever I get at the output is that channel, and that channel is actually, there is another name for it, what is called a feature map. Okay, it's called a feature map. So each channel, so the blue is one feature map, the one back to it, that's some white color thing, right. This is a feature map, that's a feature map, and just because both are drawn in blue doesn't mean that they are the same feature maps and all, just some sort of coloring, right, that they've given. So each is actually a different feature map. And right, if you're really wondering, I mean, why do we do that? Okay, the answer is that, right, I mean, when you, like I said, okay, when you do the initial layers, right, you want to capture what are called what is typically edge related information, and you might have one channel whose filters are such that, right, no, you get all one kind of edges. It could be simply horizontal. You may have another filter that can capture all the kind of vertical edges. You may have another filter that might capture diagonal edges. So each channel, right, that you can think of is, you can kind of think of something like that, wherein the network figures out. Again, we are not telling the network, right, we are not telling that we need horizontal edges, we need vertical edges, but typically what will happen is the initial layers will try to capture edge information, which is like low level information. There is nothing very high level there, it is completely low level, and that low level information will come in terms of multiple features which you actually extract from the input image, and each filter will try to be something like the one that I showed, right, 1 1 1 minus 1 minus 1. It doesn't have to be that, but very likely that it takes a form. Some of them will take a form like that. Something could be even things that you cannot explain so very clearly. So all these, so what will happen is, right, so what will happen is so one of the hyperparameters that you have is how many feature maps you want, right. That is again a hyperparameter. That is something that you have to tell, the network doesn't know. So suppose I tell that I need 8 feature maps, that means you need how many filters now? You need 8 filters, right. That means this network has to figure out what are those 8 filters, such that when it applies, so one filter it applies on the image, it gets the first blue feature map. Then it finds out another filter, applies on the input image, gets a second feature map. Then it figures out another filter, applies it on the input image, you get 8 feature maps. Okay, so till this point, is there any sort of doubt? I mean, so the idea is that, right, you can have filters of a smaller size, but then each filter you give the power to sort of extract, right, as much as you want from the input image. And what is typically found is that the lower level for the deep network behaves in a manner such that low level at the what do you call it, at the initial layers, right, you end up actually it ends up figuring out what I think I may have some figure for that, right? So what this edge, so I think right here it is. So this low level filters, right, they are called. So low level in the sense that these are the in the initial layers, and you find the kind of things, right, which they actually find, okay. And this is a Gabor filter, okay. A Gabor is just as I showed, right, a Gaussian filter. Similarly, a Gabor is a sinusoidal modulation over a Gaussian, and this is an analytical filter, which again is meant to capture orientations. And what has been found is, even let's say inside our own system, okay, human system also, we know that Gabor like filters exist in these initial layers, what is called the V1 V1 layer. We don't know much about V2, V3 and all, but in V1 we know that roughly that's what happens in the initial layers, and turns out that Gabor like functioning is what these filters also do, even though they may not be strictly Gabor filters if you try to look at the weights, but functionally this is what they do, and each filter may capture a different orientation and so on. So for example, right, I mean, this is one filter, another filter, they are all stacked. Okay, so you can have sometimes 256 channels. Okay, it doesn't mean that you can only 8 channels, need only 8 channels and all. You can have as many channels as you want, but only thing is they should be useful. You don't want to just pile on channels, right? Now, what will happen here now? Okay, suppose we ignore this layer, right? And I want to go here, right? I want to go to my next layer, and suppose I declare that I want to see 24 filters. 24 feature maps. Let's say I want 24 feature maps in my second layer. My first layer I said I have 8 feature maps, right? In my second layer I say that I want actually 24 feature maps. Now again I need filters. Okay, now what will I do? But here I've got 8 feature maps already, right? That's the input now, right? The 8 feature map is what is going as input to my next layer, not X. Okay, X was at the input. Okay, that was the image. We acted on it. We got something out. So we have 8 channels, right? 8 feature maps. They are all going as input to the next layer. Right? Now, what kind of a filter will you use now? So what you use is a box filter. Okay. So what is a box filter? So box filter, right, will look like this. So box filter will look like this. So what you have is, right, one channel. Then behind this is another, and you want to aggregate information from all of them. Right? I mean, it's like one input. No, I want to aggregate information. See, this could have happened even at the input. It doesn't mean that at the input you get only 2D. For example, if it is a color image, you'll have RGB. You'll have actually 3 channels, not 1 channel. Okay, so it's not like at the input you will have only a 2D layer. Even at the input you can have 3 channels. But I thought to start with we'll keep it easy. But as you go inside, right, now what you need is a filter that, okay, let me just show it by a different color, that will run like this. Right, that will be the box filter. So suppose I say that my size is 5 cross 5. That means that will be the spatial extent. But the extent in terms of the depth that it goes, that will be exactly the number of channels that I had from the previous output. So that I don't have to tell. That will be automatically 8 because I have to span all of them. I can't leave anything out because I got the whole input to kind of look at. Do you guys follow this? So it will be like a box filter now. So it's box filter, but the weights from channel to channel will change. Okay, it doesn't mean that the weights, suppose it's 5 cross 5, doesn't mean that this 5 cross 5 is the same as what is being applied on the next channel. This will all vary. So eventually, right? So if I have let's say 3 cross 3 filter, and I have 8 such channels, that means I have these many unknowns. Okay, and right, this is not enough because in the next layer I'm asking for how many did I say? 24. I'm saying that I need to see 24 filters, right? Now, one box filter is for one channel. I need another box filter for the next channel. I need another box filter for the next channel. I have got 24 like that. So you need, yeah, exactly. So you need into actually 24. I mean, that many weights you will need, and plus so until now I only talked about weights. So plus the bias. The bias, as you can clearly see, is one number for one channel. Just as the weights are all constant for one channel, right? Similarly, the bias is a constant for the whole channel. Therefore, it will be so all these weights will come, right? So when you act these weights, and then when this neuron takes that weighted average, you have to also add a bias to it, right? So that bias will be actually 24. So you'll have 24 channels, right? You've got 24 outputs, so you need 24 bias there, and you need 3 into 3 into 8 to cover one box filter. And you got 24 outputs, which is like 24 box filters, plus the bias, which is like 24 biases. Is this thing clear? Because this I want you to grasp in your head. And one of the things that you might wonder is, why don't we translate? After all, right, it looks like a 3D box. Now, why don't I go like, see, I'm going like this, right? I'm doing a 2D convolution. Right? I mean, I am translating this now. See, how will I get this first feature map? I have to use this box, apply it at that location. That will only give me one number. Then I have to translate this, no? I have to move it across the whole box, right? I have to cover. But that will give me only a 2D output. That won't give me 3D, because I'm summing along the depth. Okay, so you can actually think about each one as a convolution of that filter with a respective channel and just add up all the outputs, right? Either way, it's the same. So I will get one value, then I translate, I will get one more value. That is how I will arrive at this feature map. Okay, and then I have to change my filter, then I get the second feature map, then that's how I get my 24 feature maps. But the point is that you might ask, well, I am translating horizontally, why am I not going depth wise? Why am I not going this way, right? Actually, you can also do that. Strictly speaking, that is a pure sort of a 3D convolution. But this all, the filter is 3D, but then the convolution is still actually 2D, because you are not letting the filter translate along Z. Okay, I mean, there are actually reasons for it. I mean, you know, in special cases we do, but in most of the cases we don't do that. Okay, we don't translate along Z. Okay, so that's just something that you should remember, just in case you're wondering why don't we get that. So that's why you get only a 2D map, you don't get a 3D map. If you did that, you would have already gotten a 3D map then. I mean, if I also translate along Z, right, I won't get a kind of 2D, right? I'll get actually a 3D map, 3D feature, but I get actually a 2D feature, and I kind of do this, repeat this with multiple box filters, so that I get right that many feature maps. Then if you see this figure, right, so all of this you can continue doing, and so you can go from here to here, and you can actually find out how many so the size and all we will see later. If I apply a 5 cross 5, what will happen to the size of the feature map? That is something that we will see later. But for the time being, right, you should just understand, if somebody gives you an architecture, right, you should be able to figure out what's going on there. Okay, so from here to here you can come, and then eventually, right, there is I mean, if you see here, right, I mean, you've sort of reached a 1D thing. Okay, right, so that's called flattening. So what this simply means is, if I have an image, I'll simply right, unfold it into a single sort of one dimensional sort of a quantity. There is also something else that you can do, what is called well, anyway, I mean, for the time being, right, just think of an image which is getting unwrapped, right? I mean, even if you have multiple channels, it doesn't mean just one channel. You can have multiple channels, you just unwrap it, whichever way you want to unwrap, because then the network will figure out accordingly, right, it will try to find out what should be the weights. See, you need that because eventually you are trying to solve a classification problem, right? So you need a one-dimensional layer at the output. So this flattening will happen, and after this flattening, now it's MLP after that, right? Now there is no more weight sharing. It's fully connected. Then you come down, you decide how many layers you want after that. Then eventually the last layer should have only a 10 labels. So that is clear. But in between, right, how many layers you want, that again is something that's a hyperparameter. Nobody knows. After flattening, right, should you go like 2 more layers before you actually converge to that 10 label sort of output layer, or should you be doing something else? That is all hyperparameters. Nobody knows. So each network will have something. Okay, but what I want you to take home is the fact that, right, there is a CNN, right, depending upon the problem at hand, whether it's regression or classification, it can have a connected layer also, fully connected layer towards the end. Okay, that's when it happens. Initially and all, it will all be 2-dimensional filters, but after that it will all be so here the number of parameters will actually blow up here. You know that, right, because it's fully connected. I mean, here right, you might be frugal, right, in this region, right, you would have been very frugal. Because I mean, you just have 8 feature maps, right, the 3 cross 3 filter. So if you look at the number of unknowns, it's hardly anything. You're local, you have shared the weights, so there's really a number of unknowns really very, very small. But the moment you go to a fully connected layer, right, I mean, you see that things are blowing up. Of course, here the one way the weights blow up is depending upon the number of feature maps that you're asking. The more feature maps you ask, then the filter size will also become that much bigger, and therefore you will actually increase your unknowns. But then it may still be worth it because it's still local. Right. So this locality and weight sharing is what is kind of is what is most important for a CNN, and yeah, okay, and then you can have a connected layer, which is you can have a fully sort of a connected layer also.